Hi, hello everyone. So today I'm going to give a brief overview of our WACB 2024 paper towards better structural pruning saliency by reorganizing convolution. So what's the motivation behind this paper? Like over the past few years, we have seen pruning emerging itself as an effective technique to compress and accelerate CNN models by introducing sparsity into the parameters. And there are mainly two types of pruning. Unstructured pruning just remove the parameters in ways regardless of where they occur in a model. And on the other hand, structured pruning prunes weights in groups, like channels and attention heads, thus enjoy immediate practical performance improvement. And most of the pruning works focus on developing parameter importance criterion to rank the saliency of parameters, then followed by a fine-tuning session to recover the accuracy. Some representative importance criterion are L1 magnitude, which basically just select the smallest L1 magnitude weights to remove, or based on tailored expansion of the loss. In the scenarios of structure pruning, convolution kernel norm-based criterion have been widely adopted. However, they have several shortcomings. First, convolution itself does not exhibit a very clear information flow. Compare with, for example, matrix multiplication. In terms of matrix multiplication, we could directly extract some very useful information of the system by conducting eigenanalysis on the matrix. However, in terms of convolution, the information is more implicitly encoded. And secondly, if we directly just naively evaluate the norm of the convolution kernel, then this does not capture the spatial saliency of the kernel. So what's the meaning of spatial saliency here? We define the salient position in a kernel as the position having the largest norm compared with the other positions. And in this diagram, we measure the times of each location, each kernel location being the salient position in a 3x3 kernel. So there are non-total spatial positions. And we can see in the figure here that the fifth position corresponding to the central element gets the most number of times, like being the salient position here. And there is a very intuitive understanding behind this. So in the case of zero-padded convolution, we indeed use the central elements more often than the edge and corner elements. And this phenomenon is also confirmed in another latest paper in CVPR 2023 here. But however, this spatial saliency is not captured in the current methodology, based on the convolution kernel norm, since they basically just directly evaluate the kernel norm and use a uniform weighting on each of the kernel position. Therefore, in this paper, we hope to propose a methodology that can simultaneously address both of these two issues and extract some better structural pruning saliency scores by making a better use of the pre-trained weights and convolution kernels, basically. So we propose a framework called SPSRC to achieve this by a few simple steps of reorganizing the convolution. And here's the schematics of our methodology. So given the pre-trained dense model, we transform and reorganize every convolution operation into a matrix multiplication. Then we conduct an eigen decomposition on the transform matrices and directly use the singular values as the pruning criterion. That's the importance scores. And there is also a following fine-tuning session to recover the accuracy of the prune model. And based on the norm we use on the transform matrices, we propose three variants of our method: Frobenius, spectral, and nuclear. For example, SPSRC Frobenius use and evaluates the Frobenius norm of the transform matrices as the importance score. And here is an example of how that reorganization is done. So previous norm-based methods just directly do a summation of all of the kernel elements norm. And this can be considered as a uniform weighted summation. Now, however, after our reorganization step, evaluating the Frobenius norm of the transform matrix can be considered as a weighted summation. And we can see from the weighting here, the central element K22 indeed has the largest weighting compared with the corner and edge elements, those elements that are less central. And notably, our methodology can also achieve single-shot pruning with an accurate estimation of the parameter importance. So compared with other methods, we do not need the time-consuming iterative reassessment and pruning process. In order to validate our method, we conduct many experiments on different data sets and model architectures. We use 3 different kinds of data sets, CIFAR10, CIFAR100, and ImageNet, and test our methods on 5 different kinds of model architectures, including VGG16, ResNet56, ResNet34, ResNet50, and DenseNet40. Furthermore, we also show that our methodology can combine with some other latest state-of-the-art latency pruning framework to yield to further yield more improvement. For the full results, please refer to our paper. And here I will briefly show 2 results from our paper. The first one is on VGG16 on CIFAR10. And from the table, we can see that our methods yields a noticeable improvement compared with other norm-based approaches like L1 and HRank. And secondly, we could say that our method can also be integrated with latest latency pruning framework called HELP here, and yields a more optimal trade-off in accuracy and latency on ResNet50 and ImageNet. We improved the top-end accuracy from 74.3 to 75, and also improved the speed of the pruned model by around 300 images per second. Okay, so that's the end of this presentation. Thank you.